So we're talking about energy. And how much energy is that sun putting off right now? Well, it's actually enough energy to do something pretty incredible. Right now I'm on a bit of an asphalt sidewalk. And if you look down right here, this asphalt's been here for maybe about a month. And look what's coming up right through the asphalt. Plants. That's right. There's enough energy being given off by the sun and somehow still getting to those plants. The plants are able to push their way up through the asphalt. It's kind of crazy. That's a lot of energy. Sometimes it's also about how fast you're applying your energy. Now, if I had to guess, plants don't grow very fast. So instead of growing fast, they're growing slow, doing all that work on the sidewalk over time, punching their way through. Look at that. That's just crazy.
And energy is still our topic. We're actually going to go into our first energy demonstration today. So you're going to need your demo books. So grab those if you would. Remember to take down the title. You can take down the date. It's very important you write down observations and a prediction if you think you know what's going to happen. So our demonstration for today is going to be called the comeback can. Again, if you can make a prediction based on that, by all means feel free. As it plays through the demonstration, pause it, stop it, rewind it, do whatever you want to try and figure out what's going on. Take down as much information as possible about what you see, and then we'll continue on. So let's take a look at the comeback can.
Hi, so we're back here to do a demonstration, and Jacob's going to help me with something called the comeback can. All right, we have two coffee cans, can one, can two, and we're going to see how they behave when they get rolled down the table. Which one do you got right now?
Can one.
Can one. All right, give can one a roll down the table. Can one rolls, 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 and it's off the table. Okay, Jacob, let's try can two. Same roll. It stopped. And it came back. That's weird. Try one more time. Well, that time it just stopped. But hold on a second. I'm just gonna unbalance it a little bit. And it rolls right back to you. Tell me, is that weird or is that normal?
Weird.
Okay, so this whole thing's about energy. We've got these two cans right here. All right, can one, can two. Can one rolled off the table and kept on rolling. All right, can one, not what we're caring about. Can two is the one we're interested in. All right, look down at the can. So can two had a little bit of a difference, and maybe you could have spotted it before. But can two has something right here and right here. And I didn't play a trick, I just wanted to make something called a comeback can. Now, if you can see right here, I've got rubber bands attached to a weight, all right? Now, the weight hangs down. Why? Because of gravity. All right, you see it? Okay, the weight hangs down because of gravity. When the whole can spins, the weight keeps hanging straight down, which means the rubber bands are winding up. Instead of spinning with the can, the rubber bands are kind of stuck around that weight and they're winding up. And then when the can stops rolling, it's got some energy to it. So if I wind this sucker up, it actually does a little dance. It's like I'm trapping energy on the inside because I am trapping energy on the inside. It's potential energy. In this case, it's potential energy that's trapped inside the rubber band. Up here, bud. We call that elastic potential energy. So down back there, let's see if we roll it. We roll it, and I don't know, it behaves in a weird way. Does a little bit of a shifty dance. So the comeback can is a comeback can because as it rolls, it stores energy. It had kinetic energy, and then it stops winding up. It had kinetic energy, stores that kinetic energy as potential, and then it releases that potential energy as the rubber bands unwind and it spins backwards. And then, of course, we make it do a little dance. Okay? So that's an energy transformation. Kinetic energy became potential, and then it went right back to kinetic in the other direction. Okay, there's our demonstration.
Now, hopefully you were able to make a good number of observations from what you saw, and maybe even wrote down the explanation or what you pulled from the explanation. But just in case, I want to go through it right here. So as that can is rolled forward by Jacob, the weight that is on the rubber band on the inside keeps the center of the rubber band from spinning, but the sides of the rubber band wind up. So the rubber band is winding up as the can is rolling forward. The rubber band will take all the kinetic energy that Jacob gave it by rolling it and store it as potential energy inside the rubber band, inside the spinning and twisting of the rubber band. When all the kinetic energy has become potential energy, the can stops rolling at that distant point away from Jacob, and then it began to roll backwards. Why? Because the rubber band is unwinding, and as the rubber band unwinds, it spins the can in the opposite direction, taking all that potential energy that was stored on the inside and turning it back into kinetic energy. Now take your time, pause this, and write down what you have in front of you, or write down the explanation. What I would like to do after that is, hopefully someplace on your demonstration book, I would like you to do an LOL chart for what just happened. But go ahead and pause the video right here. Take down the information. Now that you have all that information down, draw an LOL chart. Remember, it's going to be an L, that is the first chart where we're keeping track of energy, kinetic energy, potential energy, thermal, and the total energy it has. Then we identify what the system is. What is the thing we're looking at as far as what has the energy? And then we have the energy afterwards. So I would say right over here, this is going to be once Jacob rolls it. This is the picture right at the beginning when Jacob has rolled it and it's moving away. Over here, this is when the can stops moving away, that distant point away from Jacob. So before, when he pushes it and it's moving away, after, once it has stopped moving. What is the energy picture? And of course we have to identify the system. The system is that comeback can. Remember, the total energy will not change, but it's going to become something different. Is it going to be kinetic, potential, or thermal at the beginning? Is it going to become kinetic, potential, or thermal after it's stopped moving? You tell me. Give it a shot. I want to see what you have. Take a picture of your diagram and upload it once you've done the notes. Remember, you can pause the video at any time to take down information or to give this LOL chart a try. But if you're ready, we're going to move on and talk about how energy transforms from one form to another in one of my favorite things, roller coasters. So roller coasters are another place where energy is going to be conserved. It's just going to transform from one type to another based on the type of roller coaster we're looking at. Alright, so potential energy can become kinetic. Maybe you're up really, really, really high in the air. You're probably not moving very fast, but when you get to the bottom of the hill, you will be moving very quickly. All that potential energy could become kinetic. Or the kinetic energy, when you're at the bottom of a hill, moving really, really fast, takes you up onto another hill where you store the energy again as potential. It could go back and forth, kind of like this. We could watch this and we could just kind of leave it there, but actually I want to take some information, because when they design roller coasters, they have to have a good understanding of how the energy is going to change forms. What if this hill right here was shorter than that loop? Seems kind of silly that anyone would do that, because if the hill where you're getting all your energy is shorter than this loop, you'll never make it around the loop. So when people design roller coasters, they actually have to pay attention to how much energy is going into the system. Let's take a look at the actual numbers using the equations I gave you before. Remember, if we want to calculate the potential energy of something, especially when it's potential energy from gravity, we take the mass of the object, multiply by gravity, and the height. if I want to find out the energy of motion of something, the kinetic energy, it's half the mass multiplied by the velocity of the object squared. Let's apply those equations to my favorite roller coaster ever, the best one I've ever ridden. It is called the Top Thrill Dragster at Cedar Point. And when you ride the Top Thrill Dragster, you go up and you come down. It is pretty simple, but it's also very fast and very, very high, about 419 feet high. So if you've actually been to Darien Lake and ridden the Superman, the Ride of Steel, the Superman comes up to right about here. The tallest hill on the Superman is right about there. So this dwarfs the Superman. It is huge. So here's our problem. This is what it looks like when it runs successfully. I want you to feel like you're in the roller coaster. So you're strapped in, there's not a whole lot of chair around you, and you just have a straight track between you and the hill. That means you have to get up to your top speed before you reach the hill. You got to get all your kinetic energy first. We want to figure out exactly how fast do you have to go. Let's just enjoy the anticipation. Don't forget to watch the lights. When this goes green, you take off. And you are up, and you're over the hill, and you are coming back down. All that potential energy you had at the top is becoming kinetic at the bottom. And that's the ride, and it's a blast. Now when you're on the Top Thrill Dragster going up that high, you're going incredibly fast, you need to have some speed. And I want to figure out exactly how much speed that would be. So we're going to assume there's no friction on this ride. Remember, friction is a force that opposes motion. We're going to get rid of all that. So all the energy is going to be conserved. All the energy you have at the top has got to be the same as the energy you have at the bottom. Now, I'm going to give you the energy number for the top. It's 1,003,520 joules of potential energy at the very top. And if we're going to put the car and rider together to find some mass, the mass that we're going to use is 800 kilograms, so car and rider. I want to know what's the kinetic energy at the bottom. So if the kinetic energy at the bottom has to be the same as the potential energy at the top, because energy is conserved, that's pretty easy. The kinetic energy at the very bottom of the ride, whether it's before you go up the hill or after you come down the hill, it's got to be that same number. 1,000,000. Takes a long time for me to write. 3,520 joules with a capital J. It's a lot of energy. Okay, so kinetic energy and potential energy the same because energy is being conserved. Given that information, how fast does a car have to go at the bottom so it has enough energy to make it up to the very top of the hill? We know it has to have this much energy, but if this is the potential energy and it has to have the same amount of kinetic energy, how fast? We're looking for velocity here. So, here's our problem. How fast does the car have to go at the bottom of the hill so it can make it up the top? This is our kinetic energy. I need you to go back and look at the equations I've given you. The equation I gave you for mechanical potential energy says that kinetic energy is 1/2 the mass multiplied by the velocity squared. Now we have the kinetic energy, and I said the mass we're going to use is 800 kilograms, so we can plug those two in. Now I have 1,003,520 joules is equal to 1/2 times 800 kilograms times the velocity squared. It's time to start using some of that algebra that you've been learning with Mrs. Stewart or Ms. Bort, or Mrs. Bort. So, let's start. If I want to get the 1/2 by itself, I'm going to go ahead and multiply both sides of the equation, because whatever I do to one side of the equation, I have to do the other. I'm going to multiply both sides of the equation by 2. When I multiply this side by 2, I get rid of that half. So these two are going to like take care of each other. Then I want to get velocity by itself, remember. I'm going to go ahead and divide both sides by 800. I got to find a better way to draw on this. So I'm dividing both sides by 800. This is just going to be calculator work. Whew. So if I were to plug that into a calculator, what I would have right now is the velocity squared is equal to 2500 and 8.8. So 2500 and 8.8. And the units are going to be meters squared over seconds. Whoa, where'd the top of the S go? Squared. So it's just the units. I take a joule and I divide it by a kilogram. Divide it by this 800 kilograms. I'm going to get meters squared per second squared. But I can't stop there. I need, let's see here. I need to take the square root of both sides because I don't want v squared, I just want v. And when I do that, I find that v is going to end up being 50.1 meters per second. Now, to give you some context, that is half a football field in a second. That's quick. How quick? That's 120 miles per hour quick. When you're riding this roller coaster, you don't want it to be raining because rain can hurt. You better hope there's not a lot of bugs. Just imagine all those bugs smacking into your face at 120 miles per hour. That's not pleasant. That is extremely quick. The speed at the bottom of the roller coaster is 50 meters per second or 120 miles per hour. Now, what happens? What happens if you're on that ride and for some weird reason, I don't know what, but for some weird reason, you don't go fast enough before you hit the hill? What happens then? Well, I am so glad you asked. I want to show you what happens then. Here we have that exact same Top Thrill dragster. We have a news reporter who is on the front trying to take a ride. Let's take a look at what happens. Now it looks like they're going pretty fast, and they are, but they're not going fast enough. Yeah, that's right. It rolls backwards. Now, it's designed to be able to handle that. You're not going to crash or anything, but it's going to freak you out. You better believe it. Here is where I will leave you. Make sure you're taking those notes. I want to have a picture, if you would, of your completed demonstration booklet for the demo that we saw, along with that LOL chart. If you have questions, feel free to email me. If you want to set up a meeting and you don't understand something, you want to ask me directly, and I can totally set up a Google meeting for you if you want. I've been doing a lot of those with the seniors. Either way, I hope you enjoyed the video. Have a good weekend.